So that's correct. Today I'm going to be talking about quantum homomorphic encryption, which is a quantum variant of a well-known classical encryption task. And this is joint work with my supervisor, Christian Schaffner, and with Florian Spillmann. So let's start with a small motivating example to get a feel for what the task of homomorphic encryption is, just in the classical case. So consider the following scenario. We have Dora the explorer. As we all know, she goes on a lot of adventures every day. She meets a lot of interesting creatures and animals. And what she would like to do is she would like to assign tags to those pictures, describing what is on them. So sheep for the picture on the left, fox for the picture on the right. She could do this, of course, manually. But ideally, what she would like to do is she would like to sort of outsource this computation. And she happens to know that there is a party, Google, that has an excellent image tagging algorithm. So what she would like to do, and what homomorphic encryption would allow her to do, is the following. She would like to encrypt her pictures, keep the secret key to herself, and send to Google only the encrypted version of her images. So Google would not be able to see what is on those pictures, but if the encryption has this homomorphic property, what Google would be able to do is compute on this encrypted data any function, so for example, an image tagging algorithm. So from the encrypted input data, these pictures, he would be able to produce the output of some image tagging algorithm. In this case, the encryption of the tags sheep and fox. And then at the end, he would be able to send it back to Dora, and she still has her secret key, so she can just decrypt the answer she got back from this evaluator Google, and there she has the tags to these pictures as she desired. So this is just some intuition. First, I'm going to make this intuition a little bit more formal, define exactly what we want from homomorphic encryption scheme, both in the classical case, and also we want to see what changes if we want to upgrade this to a quantum setting. Then I want to discuss some previous results, and in particular, there's one result that almost achieves what we want, that I want to discuss in a bit more detail, because then in the final part of the talk, our new result is going to be an extension of that previous result. So first, the little bit more formal definition of homomorphic encryption. Homomorphic encryption scheme consists of 4 polynomial time algorithms. They have to be efficient. The first one is key generation, which generates not only a public key for encryption and a secret key for decryption, but also a third key, which we call evaluation key, and that one will be used later on by Google or the evaluator to evaluate the function. Then secondly, we have to have some sort of method for encryption. So we take the public key, this round lock over here, we take some input X, and we produce some sort of encryption of that input. And of course, that encryption has to be secure for some notion of security. Then thirdly, the most important algorithm in designing this homomorphic encryption scheme is the evaluation. The evaluation, as we saw before, it takes an encryption of the input, and it produces an encryption of the output. And along the way, it can use as a reference this evaluation key that I mentioned earlier. And then finally, not surprisingly, we have to have some method for decrypting the result. So we have the secret key, the encryption of the result, and we produce the plain text result. And there's one extra constraint that we put on the decryption function, which is that it is compact. And all this means is that the amount of work that we have to do for this decrypting should be independent of the complexity of f. So if f is a more involved function, so the evaluation would take longer, but then still the decryption, the amount of time we spend on decryption should not scale. And we'll see in a moment why this is important. So we have these 4 algorithms, and if we want to design a homomorphic encryption scheme, we need to basically define these 4 algorithms and prove that they are secure and compact, and also that they run in polynomial time. So what changes if we go to a quantum setting, if we want to consider quantum homomorphic encryption? The setting is actually very similar, and only the obvious things here change. So instead of some classical plaintext X, we now work with some quantum state, psi. I've written it as a pure state, but in general it can also be a mixed state. So our data is now going to be a quantum state. And then, of course, also the functions that we're going to evaluate on this data is not going to be a classical function anymore, but some quantum operation. And we work in a circuit model, so we consider some quantum circuit. And a final detail that's going to change here is that also we'll now allow our evaluation key to be a quantum state. So the public key and the secret key should still be classical, but the evaluation key, which is going to help the evaluator during this third procedure, can now be a quantum state. Okay, so now we know what quantum homomorphic encryption is, or homomorphic encryption in general. Let's have a brief overview of some previous results. For the classical case, I'm going to be very brief. Basically, it's been solved by Gentry in 2009, was the first to show that classical homomorphic encryption, or classical fully homomorphic encryption was possible. And since then, there have been some improvements over the scheme in terms of efficiency, but basically all we need to know for this talk is that classical homomorphic encryption is possible, and it's possible under computational assumptions that are considered quantum safe for now. Then for quantum homomorphic encryption, there were only partial results, and I want to start with giving a few very trivial schemes that are obviously really not what we want. The first one being just not encrypting at all. So Dora would just send her images or other data as a plain text data to the evaluator. The evaluator would evaluate the function or the quantum circuit and send it all back. Obviously, this is homomorphic for any function because you can just evaluate any function. It's compact because there's no decryption to be done, but it's not secure at all. At the other end of the spectrum, we can encrypt our quantum data using this quantum one-time pad that was mentioned in the previous talk as well, which is information theoretically secure, so it's very strong security, but the evaluator would not know what to do with this data. He would just sit there, have this completely mixed state in his hands, and not be able to evaluate any function on it, except for maybe some very trivial like identity function or something. So what he can do then is just send it back and say, okay, I cannot do anything with this. This results in this scheme here. Or alternatively, what he can do is he can sort of cheat, and he can send the quantum state back along with some classical description of the circuit that he would have liked to evaluate on it. Then the client, Dora, she can just decrypt the state first and then apply the circuit herself. This feels like cheating. It is technically, it's homomorphic and it's secure, but we violate this compactness requirement where the amount of work in the decryption should be independent of the complexity of the circuit. And this is also why this compactness requirement is so important in order to prevent us from designing schemes like this. A slightly less trivial scheme is the Clifford scheme. It has been around for a while, and basically this scheme, it is homomorphic for all Clifford circuits. Just as a recap, Clifford circuits are the circuits that are comprised of these Clifford gates, so the phase gate, P, Hadamard, and the C.NOT. But for, as we all know, for universal quantum computation, we also need this T gate. This Clifford scheme is computational security. It's built on a classical homomorphic encryption scheme. And it works for all circuits that contain only these Clifford gates and no T gates. So the challenge here is to sort of find a way to deal with these difficult T gates. And in the past year or so, there have been several attempts to do this that have been partially successful. So, for example, Broadbent and Jeffrey last year at Crypto, they presented two schemes. One of them can deal with a constant depth of T gates. So in terms of the layers of the circuit, a constant number of layers can contain T gates, which is already a step forward from the Clifford scheme. And an alternative scheme that they presented can actually deal with arbitrary quantum circuits, but then it's not completely compact anymore. It's a lot better than this trivial scheme that we see in the top, but still it's not exactly what we want yet. And this is all under computational assumptions. And an alternative approach by Ouyang, Tan, and Fitzsimmons presents an information theoretically secure scheme that's based on techniques from quantum error correction codes, and they can also deal with a constant number of T gates. but there are some caveats there where you need more copies of the input. And also it's known for a few years now, a result by Yu and others that shows that information theoretically secure, fully homomorphic encryption is not possible in the perfect case. So this is some previous results, and in particular I want to focus a little bit more on this Clifford scheme here and explain what it looks like, because basically our result will be an extension of that Clifford scheme. So for the Clifford scheme, we need two ingredients. The first one is the quantum one-time pad. We just saw it defined in the previous talk, but I'm going to go over it again really quickly. So for encryption, what we do is we pick two random bits, A and B. This is going to be our key. And we pick a single qubit, and we encrypt the qubit by applying a bit flip condition on A and a phase flip condition on B. And that produces this encrypted quantum state psi. And we do this qubit by qubit. So for every qubit, we have to pick two key bits. And then the decryption is really simple. Actually, we just do the same operation again. So we apply the same Pauli operation, x, a, z to the b, and we get back our original qubit. And this form of encryption completely hides the input state as long as you don't know the key A and B. The second ingredient that's used for this Clifford scheme is any classical homomorphic encryption scheme that is safe against quantum adversaries. And as we've seen before, these types of schemes do exist. So we can just plug and play with any encryption scheme that comes up. And the idea is the following. So we have our client, Dora, and she has this quantum state. And she wants to do some computation on it, or have Google do some computation on it. So what she does is the following. She picks some random quantum one-time pad key and encrypts her state using this key. And then she sends it over to Google. Google cannot see what's inside this state, but let's suppose he wants to evaluate the Hadamard gate on this state. And what we're going to do is actually we're going to just apply this Hadamard gate to the encrypted state. So instead of to the plain text, we're going to apply the Hadamard gate while this Pauli encryption is still in the way. And with some computations, we can see that actually we end up with a valid encryption of the result. So we end up with a valid encryption of Hadamard applied to psi. Only if you pay close attention, you'll see that the key that used to be A, B has now changed to B, A. So the key is different. So if all we were doing is just having Google apply this Hadamard gate to the state, even though we end up with a valid encryption of the result, if we just send this back to Dora, she cannot decrypt it because her key does not match anymore. So how are we going to get past this? It's a very neat trick, actually. So Dora has this secret key here, A, B, and instead of just keeping it for herself, what she's going to do is she's going to use this classical homomorphic encryption scheme to encrypt the key to the quantum one-time pad. Remember, the key to the quantum one-time pad was just two classical bits, so we can use this classical homomorphic encryption scheme to encrypt it. And then we get a classical secret key that she can keep for herself. She sends this over to Google. Google does not know what the key is. He cannot see it because it's encrypted. But what he does know is that he just applied a Hadamard gate. And so he should somehow, he knows how this key is going to be updated. If it was A, B first, now it should become B, A. So he can, using a classical homomorphic evaluation, he can just evaluate an update function. Update function, in this case, for the Hadamard gate, would swap the two values. So starting with an encryption of A, B, he can produce an encryption of B, A. And for the other Clifford gates, we can do a similar thing. So the update rules differ slightly, but they're all simple linear functions. And now what we have is the following. We have our encrypted quantum state with the gate applied to it, and we have our updated key to this quantum one-time pad. And now all we need to do is send everything back to Dora. She can use her classical secret key first to decrypt the key to the quantum one-time pad, and then she can use this updated key to decrypt the quantum state that she's interested in. And now this challenge, so this was this Clifford scheme that's been around already for a while, and the challenge is now how can we evaluate a T-gate? So first let's see what's the problem here. So if we want to do just the same thing that we're just doing before, we just apply this T-gate to our encrypted state, what happens? It depends on the value of our key. So if the first bit of the key, A, if it equals 0, then everything is fine. We can just apply it, and we end up with a valid encryption of the result. However, if the first bit of the key is 1, so A equals 1, then something weird happens. You can verify this by the computation, but we do end up with a valid encryption of the result, but now there's an error term on it. There's this extra phase gate on it, and we don't want it to be there. We cannot continue with the computation until we remove it. So the challenge now becomes, how can we apply a correction gate, the inverse phase gate, if and only if A equals 1? Google, the evaluator, has to do this. There's no opportunity for communication with the client in between. But he does not know the value of A, and he's also not allowed to know this value of A because it's part of the secret key. So this is really the challenge. And in our new result, we find a way to deal with it in such a way that we can evaluate any quantum circuit with a polynomial number of T-gates. So contrasting with the previous results, we can really evaluate a polynomial number of T-gates and thereby evaluate any quantum circuit of polynomial size. And thereby, the technical term for this is that it's leveled quantum fully homomorphic encryption. And because we built our scheme on top of this Clifford scheme, we inherit all the computational assumptions that are needed for the Clifford scheme, but we don't need any other computational assumptions. So just in the final minutes, just to give a very brief overview of how we do this, we design error correction gadgets. We use one gadget for every T-gate. And these gadgets, roughly, they look like this. So they're going to be a quantum state. And we're going to give it to Google, the evaluator, as part of the evaluation key, which, if you remember, was now allowed to be a quantum state. So it's just going to be some number of qubits. And during the key generation phase, we entangle those qubits in a pairwise way. And the structure of the entanglement is determined by the secret key. So we just have some deterministic function that, given the secret key, we can decide on some structure of how to entangle these qubits with each other. And this resulting state is going to be the gadget. And then to use the gadget, also, additionally, we on one of the qubits at the end, we apply this inverse phase gate that we want to apply to the state. So then to use this gadget, basically what the Google has to do is also he has some sort of deterministic function that, given the encryption of A, gives him some instructions for how to measure on this state. So he performs some Bell measurements on the state according to the encryption of A. And we design it in such a way that if he now inputs at the top, using another Bell measurement, an encryption of the data qubit that does have an error on it, so A equals 1, so the encryption of A is also something that would decrypt to 1, then you can follow, basically the state is basically teleported through the gadget, and you can follow the path, and you see that it passes this error correction gate in the end. And so what comes out is the resulting state without the error. Whereas if Google would start with a state without an error, so A equals 0, we don't get an error, then also the encryption of A is going to be a different classical value, and so the measurements that he's going to do are also going to be different. The instructions are different, so in that case, the quantum state is routed through the gadget in a different way, and if you can follow it, it now doesn't pass this correction gate, and it just comes out on the bottom without this inverse phase gate being applied to it. So this gadget allows us to remove this phase gate if and only if it was present. And for the expert in the audience, basically what this gadget does in spirit is it computes a permutation branching program for the decryption function, where the instructions that depend on the secret key are already done in the key generation phase, and the instructions that depend on the encryption of A, they are executed during the evaluation phase. So a very brief overview of our scheme, just to recap. We needed to define these 4 algorithms. The key generation algorithm, first we generate the classical keys for some classical homomorphic encryption scheme. Then we generate a number of these gadgets. We need to generate one for every T-gate, because if we measure on this state, the state is going to be destroyed. So these squares, they represent this entangled state that I just presented. For the encryption, we first encrypt using the quantum one-time pad. Then we encrypt the quantum one-time pad key using some classical encryption procedure. For the evaluation, for the Clifford gates, it's actually quite easy. We can just classically update the keys. And for the T-gates, we have to use one of these gadgets. And this is why we can only evaluate a polynomial number of T-gates, where the polynomial is in the security parameter for the scheme. And for the decryption, first we decrypt the updated key classically, and then we use this updated quantum one-time pad key to decrypt our quantum state and to get the result. So briefly for some future work, one direction for future work would be to upgrade this scheme to some non-leveled version so that we can do an arbitrary number of T-gates. We're not using these resource gadgets and we're not using them up anymore. But I think more interestingly is to see what kinds of things follow in the quantum world from homomorphic encryption that are known to follow in the classical world from quantum homomorphic encryption. So two examples would be multi-party quantum computation or quantum obfuscation, and many more. Thank you.
We have time for a quick question.
Hi. So your decryption phase is compact because you only do measures. Yeah. On the other hand, your key generation phase is kind of not compact because the number of gadgets you need depends on the circuit you are doing. Do you think it will be possible to also have like a compact key generation phase?
We don't know if that's possible. We've been thinking about it, and it's not known if there's maybe some minimum number of quantum state that you need to do this. So it's true that we move a lot of the work from the decryption phase basically to the key generation phase. And the only difference here is that in this case, the key generation phase is not dependent on the input. So there is the key difference there. It would be interesting to see, because if we can sort of reduce the amount of work done in the key generation phase, then we would have this non-leveled quantum fully homomorphic encryption scheme. That would be amazing.
Let's thank both of our speakers from this morning.